Chapter 33, Problems on Lenses and Optical Instruments. Question 1, it gives you the power, it's negative, and therefore it's a diverging lens. And since it has negative power, it has to have negative focal length. So it's a diverging lens. 12.5 centimeter is the distance of the object. And the height of the object is also given. So from the power is always 1 by focal length, but then the focal length has to be in meter when you use this formula. So if you can find the focal length, you're going to get it in meters, and it's 0.125 meter, which is 12.5 centimeter. Negative means it's a diverging lens. So use the lens equation and make di the subject. Substituting the numbers. Remember, DO is always positive. DO, the object distance, is always positive. F is negative for a diverging lens, and F is positive for converging. Now, since you get DI as negative, that means it's a virtual image. And you have the two formulas for magnification. One is HI by HO and negative DI by DO. So you can find HI because the other three are given. Since you get HI is positive, that means it's an upright image, and of course an upright image is a virtual image. Well, question number 2, it's a positive focal length, that means it's a converging lens. And the A part says how far ahead of the film should the lens be. So that's the distance between the film and the lens, which means it's the distance between the image and the lens. So you have to find DI. And DO is given as 10 meters. So use the lens equation. Make DI the subject again. DO is 10 meters. F is 105 millimeters, so that's 0.105 meter. So that is DI, 10.6 centimeter. Now do the same for the other two distances. Exactly the same formula, just DO changes to 3 and then to 1. In the D part, what is the closest object this lens could photograph? So when DO becomes minimum, remember that DI becomes maximum, and that maximum distance is 132 millimeter, which is 0.132 meter. So now you're going to find DO. Put the value of DI max, which is Well, if it's in centimeters, it's 13.2. And the focal length is also in centimeters, 10.5. And you get the answer as 51.3 centimeter. That means if the object is closer than 51.3, you're not going to get a clear image on the film. Question 3. It's a converging lens. The focal length is positive 25. And it says it's a real image, same size as the object, so that the magnification is now -1. Why? It's a real image. Now we know that di is equal to do because magnification is 1, and the magnification is given by -di by do. Okay, so -di by do is -1, therefore di is equal to do. Once you get that, find do, and now since you got, okay, I'm trying to explain how I got di is equal to do now. Magnification -1. Why? Because it's a real image. That's how I got di is equal to du, and then you got the answer as 50 centimeter. In question 4, you have to find du. And if it's going to be a real image, it's a converging lens. Of course, the focal length is positive. There are two cases. First time it has to be magnified twice and it's a real image. Second time it's to be magnified twice again, but the image is virtual. So the difference is going to be in the magnifications. If it is a real image, the magnification is negative. If it's a virtual image, the magnification is positive. Well, F is positive here because it's a 50 millimeter. It's only a converging lens that can produce both real and image. Okay, if it must be a real image, di must be positive, and so magnification must be negative. That's m is negative di by do. That's negative 2.5. Oh, actually it's negative 2. So sorry for that mistake. I've taken it as negative 2.5. And I'm doing it for 2.5. So please change the question to say magnification is 2.5. Okay. So once you get di in terms of do, put it back into the lens equation. And find do. On top you're going to get do squared, and below you're going to get do. That's why you remain with do in the numerator, and the do is 70 millimeter. Now for the B part, the image is virtual, so that means di is negative, magnification is positive. So now you get, going back over the whole process like before, you get di is negative 2.5 do. Plug it back into the lens equation, rearrange and calculate. You get it as 30 millimeter. In the fifth question, DO and the focal length is given. First time you take it as a converging lens and you have to find where the image is, so you're looking for DI. So make DI the subject. That's DO. Focal length is positive. It's 0.135 in meters. You get 0.1506 meter. Magnification HI by HO, which is negative DI by DO. So you have DI and you have DO, so you can find HI. And you get HI is 0.324 meter. So that's actually 32.4 centimeters. So that's highly magnified. In case B, you take it as, going back to that first. See, since I had kept it in centimeters, you get the final answer in centimeter. Because it doesn't matter whether 0.1506 and 1.30 both are in meters. That's what I'm trying to show. So as long as 2.80 is in centimeter, you get the final answer in centimeter. So actually it's a smaller image. In the second part, you want to use a diverging lens, and a diverging lens can only produce a virtual image. F is negative. The formula is the same. The only difference, focal length is negative. Once you get DI, excuse me, you find the magnification, same process, same formula. DI in meter, DO in meters, but HO is in centimeters, so you will get the answer in centimeters. Now notice that the magnification is positive. That means it's a virtual image. Magnification negative, it's a real image. Okay. That takes us to question number 6. This person needs to read a computer screen at 55 centimeter, but his near point is 105 centimeter. So that means when the object distance is 55 centimeter, the image must be produced at 105 centimeter. So he'll be able to see clearly. And for that, you're going to need a convex lens. Okay, the screen is placed at 55 minus. You always got to take that 1.8 centimeter away from each distance, because that's the lens side distance. So it's 53.2 centimeter from the lens. That is DO. And the image is to be produced. It's going to be a virtual image. And that's to be produced at 105 minus 1.8, which is 103.2 centimeter away. And And power is 1 by F, and we have the formula for 1 by F. Remember, F will be in meters. Therefore, DO and DI both should be taken in meters. So that's 0.532. DO, DI is negative. How do we know it's negative? Because it should be a virtual image. So you get power positive, which means it's a converging lens or a convex lens. Taking us to the 7th question. This guy is definitely nearsighted because he needs a converging lens. Did I say converge? It is a diverging lens, unlike in the last case when it was a converging lens. Let me correct that. Nearsightedness is corrected using a diverging lens, while farsightedness is corrected using a converging lens. Well, in this case, the person is nearsighted. His far point. See, far point should be, he should be able to see up to infinity. So that's why I've written a statement that says an object at infinity. Therefore, we now know DO is infinite. And use the lens equation. Keeping that in mind, 1 by infinity gives 0. So you end up with 1 by DI is equal to negative 4.5. And that's the power, which is 1 by F. And so DI is just 1 by that, which gives you negative 0.222 meter, which is negative 22.2 centimeter. So his far point is, when you take the difference, take the magnitude in this case. Otherwise, it makes no sense. So his far point is 24.2 centimeter from the eye. That means he could not have seen anything beyond that. But when he uses these diverging lenses, his far point is taken from 24.2 centimeter all the way up to infinity. He's able to see clearly. Question 8. This guy can only see between 25 and 78. So when DO is equal to infinity, his image must be produced at 78 centimeters. Use the lens equation. DO is infinite, DI is 0.78 negative. That's why it's in front of the eye. It's a virtual image, that's why it's negative. So you need negative 1.282 diopter for that. And then to find the new point, you have to find DO, and DI is 25 centimeter now. So we're going to look at what's the object distance so that the image is formed at 25. Make DO the subject. 0.37 meter. The ninth question, quite simple because it talks about an astronomical telescope for which the magnification is negative FO by FE. Here you have both. It's only that the power of the eyepiece is given, and that's 1 by FE. So that's why the formula became negative FOPE. Everything has to be in meters whenever you work with diopters. So you get it as negative 26 times magnified. The last one, we have two more. Okay, the 10th one. See, if ever it says for a relaxed eye, that means the image is formed at infinity. So the final image is at infinity. In which case, the total length of the telescope tube will be equal to the sum of the focal lengths, which in this case is given as 78 centimeters. So now use the formula for magnification, but substitute for FE as L minus FO. All distances are in centimeters now. Get it as negative 30 times magnified. Alright, 11th one. The radius of curvature of this reflecting concave mirror is given. So you can find the focal length as being half of that. And because it's a converging mirror, its focal length is positive. So now you have the focal length and of both. The objective is 2.8 centimeter, that's 0.028 meter. So this is capable of magnifying negative 114 times. Negative, again, remember, shows that the final image is a virtual image. Now that brings us to the last one. It's a relaxed eye. The two lenses are 1.25 meter apart. So remember, relaxed eye, the final distance, final image is at infinity. And again, the length or the distance between the two lenses must be equal to the sum of their focal lengths. In this case, the total magnification is given as 120. So the distance between the lenses, 1.25 meter as given, which is equal to FO plus FE, and magnification is negative FO by FE. Substitute for FE as L minus FO. And now we have to rearrange and make FO the subject. Distribute the M's there and then bring the FO terms together, being very careful with the sign. Finally, you get FO onto one side and substitute. Magnification is negative 120. Negative 120. Remember, it's a virtual image for a telescope. The final image is virtual. You can see it, but it cannot be produced on a screen. So once you get FO, you can find FE. As being very small, obviously, it's 0.01 meter, and that's why the magnification was about 120. Thank you.